Hello everyone, welcome back to today's program. I'm Smiling Rockets. For a very long time in the past, when we talk about AI, we often associate it with those cloud data centers with massive amounts of data and powerful computing power. This is what we know as centralized intelligence. It's like an omniscient super brain collecting data from all directions, conducting centralized processing and analysis, then feeding results back to terminal devices. This model has achieved tremendous success in many scenarios. For example, search engines, recommendation systems, large language models, and so on. Now, imagine such a scenario. There's an advanced drone. It relies on cloud-based AI for high-precision target recognition and complex path planning. In open areas with good network signal, it performs exceptionally well, able to complete tasks accurately. But once it enters deep mountain canyons or areas with poor network signal, it may lead to the drone being unable to receive cloud decision instructions in time, resulting in operational delays, sluggish responses, even dangerous situations. At this moment, the super brain far away in the sky seems beyond its reach. Similarly speaking, a drone, but equipped with local AI processing units, it doesn't need to upload all sensor capture data to the cloud, but performs real-time environmental perception locally, target recognition, and path planning. Therefore, it can respond to surrounding environment changes at millisecond level speed, flexibly avoid obstacles. Even in complete absence of network connection, it can fly autonomously and safely. These two completely different performances lead us to the core issue we're discussing today. Must intelligence completely depend on huge and distant cloud servers? Local AI, or what we call distributed intelligence, edge intelligence, is revealing a whole new possibility for us. Here, we have a table that allows us to more clearly compare the architectures of these two types of intelligence. How to implement powerful AI functions on edge devices with relatively limited resources. This is precisely why TinyML technology emerged. Next, we will deeply explore the key technologies for implementing local AI, especially the roles of main control chips and sensors, and how TinyML works. First, let's look at the brain that drives local AI, the main control chip. The rise of edge AI has spawned a profound revolution in the main control chip field. It must achieve a delicate balance among computing power, power consumption, cost, and size. Today, we focus on one device that's widely popular among makers and AI education, the Unihiker K10 Learning Mainboard. This single-board computer that looks like a mini smartphone, its core features Espressif Systems ESP32S3 chip. The ESP32S3 is a low-power controller specifically designed for IoT and AIoT applications. It's not just a simple processor, but a highly integrated system on chip, or SoC. The Unihiker K10 Learning Main Control Board is not just a development board. Everyone, pay attention. It integrates a screen, multiple sensors, and portable expansion interfaces, providing an out-of-the-box platform for learning and practicing TinyML. Besides the Unihiker K10 Learning Main Control Board, we also see products like the Unihiker Mac 10. This Python main control board, as a sister product, it may have different focuses in hardware configuration, but both reflect the trend of empowering edge devices with AI capabilities. If main control chips are the brain of local AI, then various sensors are its eyes, ears, and antennae. The rise of local AI has also greatly promoted the development and innovation of sensor technology, forming a huge and diverse sensor ecosystem. Let's look at several sensor modules that play key roles in local AI applications. First is our Gravity Offline Speech Recognition module. It has built-in speech recognition chip and algorithm and can complete specific speech instruction recognition locally on the module. No internet connection needed, no need to rely on external main control for complex speech signal processing. Users can pre-record through simple configuration tools or serial commands, or set keywords or commands that need to be recognized. For example, we say turn on lights, turn off lights, play music. The module will store these acoustic features. During operation, it continuously monitors environmental sounds. Through built-in algorithms, it compares captured speech with pre-stored features. Once matching succeeds, it outputs corresponding recognition results or trigger signals through I2C or UART interfaces. This is very suitable for smart home control, for example, offline voice switches, appliance control, toys or portable devices requiring language interaction, and some industrial controls, teaching, or specific scenarios with high requirements for network connection or privacy. Next, let's introduce another star product, Huskilens. This is our AI vision sensor. It's not just a simple camera module, but an intelligent entity integrating eyes and a visual brain. It can locally, independently run multiple mainstream AI vision algorithms, achieving true edge vision intelligence. The one-key learning function is one of its major features. Users, without complex code, just need to simply press once. The sensor looks at the target a few times that you want to learn. For example, a specific face, a specific object, or a specific color. It can complete rapid model deployment locally, greatly lowering the barrier to AI vision applications. Besides input type perception sensors, output type modules are equally important in building complete interactive experiences. For example, this Gravity Chinese English Speech Synthesis Module V2. It can convert text information into clear and natural voice output, letting devices speak. In local AI applications, it can work with speech recognition modules to achieve more natural voice dialogue, or broadcast AI vision sensor recognition results through voice. This is very practical. Now we have powerful main control chips and sensitive sensors. But how to successfully transplant these AI models, usually very large in size and computationally intensive, from cloud training to these relatively resource-limited edge devices? This depends on our TinyML technology stack. It's like magic. It can fit an elephant into a refrigerator. TinyML, as the name suggests, is the technology that shrinks machine learning models to run on low-power, low-cost embedded hardware like microcontrollers. It's not a completely new machine learning algorithm, but through model compression, such as pruning, quantization, knowledge distillation, dedicated hardware acceleration, and efficient inference engines, it makes originally large and complex AI models become small and efficient. They can run smoothly on microcontrollers with only hundreds of K or even dozens of K memory. Power consumption can even be as low as milliwatt level. TinyML is like a crucial bridge. Through this series of careful design and optimization, it successfully empowers those ubiquitous tiny devices with powerful AI capabilities, making them smarter and more autonomous. Next, we will demonstrate through 3 specific projects to show everyone how local offline AI and TinyML go from concept to reality.
Only 3 steps to voice control your Arduino Uno. All we need is an offline voice recognition sensor, an Arduino Uno with its expansion shield, and a fan. Connect the sensor. Program Arduino Uno with IDE. And run the program. Hello, robot.
Yes, I'm here.
Turn on the fan.
Okay.
Under the control of the offline speech recognition module, it smoothly completes various corresponding instructions without any delay. All this can be completed without an internet connection. Your voice instructions and control data are only processed on local devices and won't be uploaded to the cloud. If this is in a place with very high privacy requirements, it greatly reduces privacy leakage risks. Next, in this project, we will recognize a specific face. For example, I'm the owner, or recognize a stranger. Here we can ask our staff to play the intruder. Then we can display recognition results on our Arduino on our screen and trigger alarms. Before entering AI development, many people start with traditional Arduino development boards like this DF Robot Arduino starter kit. It comes with a UNO main control board, LEDs, servos, buzzers, and 35 commonly used components, plus 30 illustrated tutorials. Step by step, it guides you to master circuit and programming basics. Although it's not an AI main control, it's perfect for beginners with zero foundation to understand how sensors work, how to control actuators, and lay a solid foundation for subsequent AI learning. Now let us demonstrate. First, in our Arduino beginner kit, we take out these contents. Here I have prepared related items. Then we connected the green LED and red LED and buzzer. Then we connect our Arduino. Very simple. Next, we write a short program. Open our computer. Plug in. Here, I have already written the program. Through our Mind Plus, we upload this program to the device now. Good, code is ready. Let's learn my own face through simple learning. Okay? At this moment, when it sees me, the green light will turn on. The green light will turn on. Please ask our staff to come. Yes, if it sees people not in the recorded environment, the red light will turn on. Then this buzzer will sound, indicating intruder entry. Okay, good. The first two projects, we saw local AI applications in perception control. The third project, we will focus on human-computer interaction. We'll show how to use the UniHiker K10 learning main control board to achieve gesture recognition, letting devices understand your body language, thus achieving more natural and intuitive interaction.
Today, I'll show you how to use the UniHiker K10 Magic Wand with an AI model deployed to conduct motion inference and judgment. When using it, press the button on the Magic Wand and draw a triangle within 2 seconds. When the Magic Wand recognizes the triangle drawing motion, the light strip turns green, and the magic hat sways from side to side. If you wave the Magic Wand horizontally, the magic hat stops swaying. This is our AI Magic Wand. Thanks to the powerful computing power of the UniHiker K10 and its onboard acceleration sensor, it can accurately distinguish waving motions.
We utilize Edge Impulse, which is a powerful AutoML platform that greatly simplifies the TinyML development process. Through appropriate tools and methods, this can also be implemented on resource-limited edge devices, bringing richer, more natural interactive experiences to smart devices. Through today's sharing and project demonstrations, I believe everyone has a deeper understanding of the evolution from centralized intelligence to distributed intelligence, and the key roles played by TinyML and local offline AI. We saw that intelligence is no longer exclusive to the cloud. It's penetrating into every corner of our lives in a more accessible, efficient, and secure way. Thank you for watching. In the next episode, we will conduct AI project practice. Remember to follow us and share with people you think need to know this content. Also, feel free to comment. See you next time. Bye-bye.